compressed version of that talk. So really, there's 3 steps here. So we want to, okay, so hypergraphs, we're interested in hypergraphs because hypergraph, can represent more complex data than graph, fair enough. And we are in the process of developing tools. There's not that many tools available for the analysis of data represented as hypergraphs. So one of the main take-home message here is that our data is almost always unsupervised, at least in the area that I work in. So unsupervised techniques is what we're looking at. And one of the very important algorithm in unsupervised learning is clustering, grouping, like things together, clustering of your vertices unless otherwise stated. So I'm going to be talking about clustering hypergraphs in the sense of grouping vertices that are, sharing a lot of hyperedges and things like that. But there's really 3 steps. Modularity as an objective function, we're going to go from graph to hypergraph. So we have generalized that notion to hypergraph. This is previous work. Then I'm going to mention a few words about clustering hypergraphs, a couple of algorithms that exist as we speak, but then our solution to go to a more hypergraph-based solution for clustering hypergraph. And you're going to see what I mean as we go along. Okay, so we have a graph, we have nodes, we have edges, fair enough. Graph clustering, in this case, by graph clustering, I mean a partition of the vertices. So it's a partitioning. The term graph clustering is used all over the place in the field. So, but really think of partitions, okay? No overlaps in this case. And okay, so to build graph modularity, we need to, so it's this guy. So we need to talk about the Cheng-Lu model. So the Cheng-Lu model is one of the simplest model after the Erdős-Srény for graphs, where basically we have a degree sequence that we want to follow at least in expected value. So we have a graph, nodes, edges, fair enough. So we sample edges. The edges are sampled with respect to or proportional to their degree, okay? So at the end of the day, you're going to have random models that have the expected degree distribution from where you started. So let's descript G be the distribution of such random graphs. I'm always tempted to go press the button here. So the modularity is a very commonly used objective function for graph clustering. Can be written as follows. So it is the difference between the proportion of edges that are completely within one of the part. So that's E.g. AI are all the edges that are completely within part AI, so both vertices. This is what you call the edge contribution, that's the first part, minus the expected value of this term under the Cheng-Lu model, okay? So, and we refer to this sometimes as the degree tax if you want. Okay, so it has some properties, it has some advantages, it has some disadvantages, but we're not going to go through that today. Let's just say it's a very commonly used objective function for clustering graphs. Okay, so again, in our previous work, and I'm going to go very quick about that, we generalized the notion of Cheng-Lu model for hypergraphs. It's not hard to do. And the one thing we needed to introduce is the notion of the edge size. But basically, if you start from a reference hypergraph or you're given some degree distribution, well, in the same way, you can, have the reference to the distribution of edge sizes, or you can pick your own choice for edge sizes. So that's one of the new ingredients that needs to be added, but we can show that the expected degree under this family of random hypergraph model, Cheng-Lu hypergraph model, is the degree that we started with or that we want, okay? So this generalization of the Cheng-Lu is going to be our degree tax for hypergraph modularity. Now, and this is the one point where I'm going to spend a minute or two explaining. The main difficulty in we're aiming at communities here, one clustering communities, right? So in a graph, it's easy. An edge is within a community, both points are in the community, or it's between two communities. So it's within or it's between, it's community or it's noise. You can see it, very easy, binary. What about hypergraph? What about hypergraphs? When is a hyperedge part of a community? Well, okay, this is debatable, but at the very least, we're going to require that C or more, more than half of the vertices are in the same community. Why is that? Well, to avoid the possibility of having, you know, something that's ill-defined. You don't know which community because half are red, half are blue. Then, you know, which is it? So if you impose the fact that you're going to call an edge of type CD if they have exactly C member in community AI where C is strictly greater than D over 2. Okay? And then given that, you can define your modularity essentially by slices. Okay? So basically, for each size of, for each edge size D, for each value of C strictly greater than D over 2, you basically define the modularity as the difference between the number of such edges minus the expected number under your random model. As simple as that. And then you can talk about the generalized hypergraph modularity, where you basically sum your slices, okay, with some parameters WCD that are entirely up to you, okay? There are some natural choices, one of which in some applications, maybe I want to consider an edge to be part of the community if and only if all the vertices are in that community, and only if that, okay? Well, in this case, I'm only going to consider the DD slices, right? So C needs to be equal to D. So and the other ones are all going to be 0, okay? So those are the only slices I consider. That's an example, and that's a very hypergraph example in a way, right? Because you really need to know the structure of your hypergraph. Other possibility is some increasing function. It makes sense in some cases. So if C is close to D over 2, well, maybe this is mildly part of my community, but as C goes to D, okay, maybe I want to increase the value WCD so that, you know, this plays a higher role. It doesn't have to be linear. Pick, you know, any non-decreasing or any increasing function that you like in terms of C. And at the other end of the spectrum, majority is that you give an equal weight. So all the WCDs are equal. So as soon as you have more than half of your vertices that are part of the community, they're all the same. They all count the same in the modularity function. Okay. Sorry, that was very quick, but that's really the background we need to talk about clustering in this case. Okay. I'm going to talk about the Louvain algorithm because it's really at the basis of many algorithms, and it's at the basis of what we are proposing also. So let's take a minute or so to describe this Louvain algorithm. Okay, so we have it's for a graph. So in the Louvain algorithm, you're trying to optimize modularity, and you do so in the following way. You randomize your vertices, and you traverse your set of vertices. Okay, you initialize the problem so that at the beginning, every vertex forms its own community, okay? That's important to say. So every vertex is in its own community. Then you traverse the vertices randomly, looking at every neighbor. For every vertex, you look at every neighbor and you see, okay, if I move that vertex to one of my neighbors' community, am I improving modularity or not? And if I am, I make the move, or I make the best move I can make. And you do that repeatedly, okay, until there's no more improvement. So that would typically find small-ish communities, something like that maybe. Now there's no more improvement. You collapse the communities into nodes, and notice now there are loops, because, okay, and you rinse and repeat, right? So you do the same thing. This is why it's also called the multi-level clustering algorithm, because there's several steps where you basically build a hierarchy of community. But the one important thing to remember, every vertex starts in its own community. Okay, let's remind ourselves of that because it's going to be important. How do we cluster hypergraph? Well, I have a hypergraph now, vertices and edges or hyper edges. Well, what is done quite often is basically take what we tend to call the two section. You basically replace every hyper edge by a clique, okay? And that's a graph. You can weight it. There are different, you know, ways to weight that, to weight the graph, the edges, sorry. And then you apply your favorite graph clustering algorithm, Louvain. Leiden and ECG are improvements over Louvain for graph clustering. Easy enough. But we want to have something that's a little more hypergraphy. I mean, we want to take advantage of the fact that we do have the hypergraph structure. Reducing to the two section, we get rid of that, right? We just keep it mildly because of the weights, but that's it. So this is an algorithm that was proposed a couple of years ago. That's actually in HyperNetX, that we've coded up in HyperNetX by Kumar and others. And it's a slight refinement to the Louvain algorithm that takes a little more into account the fact that you are on a hypergraph. So you still go and build a two section and run Louvain. That's the same thing, okay? But now you're going to reweight edges in the hypergraph based on a measure of homogeneity between the parts and repeat until convergence. Okay, the idea being that if I do a first clustering based on the two section, if I have an edge where almost everything is green and there's a couple of blues, for example, here, so it's almost homogeneous, I'm going to boost its weight. I'm going to weight that up so that maybe I'm going to get rid of those two blue and they're going to become green, right? This is almost a pure community edge. So this is important, right? But this one is half and half. Forget it, you know, we're not going to go anywhere with this. This is probably not useful. That's the idea. Is it a good idea? I think it's an interesting idea. It does help a little bit. It's clustering, so you know what is the better solution is always a bit. It depends on the problem, right? But that's the idea. So you do take into account a little more of the hypergraph structure, but still you're optimizing a graph-based objective function. There's a more recent algorithm by Chodro and others called the hypergraph maximum likelihood Louvain. This one is much closer to what we are doing, okay, much closer. So it's defined for several choices of modularity, including our own definition. It is the Louvain algorithm, but instead of collapsing, you build those kind of super nodes and we do something very similar to that. There is a problem, however, in this algorithm is that it's hard to lift from the ground without small size edges. Okay. I'm going to say what I mean by that. What do I mean by lifting from the ground? This is one of the main issues with agglomerative hypergraph clustering, right? Because remember, we start with every node in its own cluster. Okay. If I only have large edges, then I'm going to join two nodes. And in the first step of this Louvain, I join two nodes. So instead of having a hyper edge of size 19 with 19 different colors, and I now have 2 red and then 17 other colors. Not very strong by any means, okay? So you're far from a majority for sure. So in other words, in order to lift from the ground, meaning start the process, start the algorithm, you need small size edges. And even if you have small size edges, there is a strong bias in the first steps that everything you're going to do, all the decisions you're going to make at first, are going to be based on your size 2 edges, maybe size 3 edges, and that's it, right? So that's a problem. So we want to get something that's more hypergraph in terms of the objective. Well, this is remarkably simple, okay? But sometimes simple is good, right? So we're going to alleviate this issue by forcing small size edges at first. How do we do that? With the two sections. Okay. And then we're going to gradually move towards a true hypergraph-based objective, right? So, well, okay, couldn't be simpler, but, you know. So we're going to start with some alpha that typically will be close to 0, which means that at first we're going to optimize with respect to, you know, the two-section modularity, but then we're going to, Q is the symbol for modularity. I use QH for hypergraph modularity, one of the many flavors that we have. And then QH2 is just a graph or two-section modularity, okay? So basically, we're going to turn the knob gradually from alpha to some initial value all the way, likely all the way to 1, because at the end of the day, that's what we want to optimize, okay? But doing that will help us, you know, lift from the ground and then make the algorithm work, right? And then from here, it's work in progress, I warn you, okay? It's very empirical and it's work in progress, but there are questions, right? Where should we start? What should be the initial value? Should we always increase or should we zigzag, to use a word that was just used? When to update, by how much, okay? Well, so in other words, we need some kind of a policy by which to vary our value alpha. And all of this is going to be based on lots and lots and lots of empirical tests. We've done a few, well, we've done quite a lot, but there's still a lot more to come. Just as a plug here, so another thing that we've been working on is this ABCD benchmark for graphs. And we now have a hypergraph version available on GitHub. This is Bogumil's GitHub account. So, so basically, it's a benchmark that is, ABCD is a benchmark that's very similar to if you've used LFR, which is a very commonly used benchmark for comparing graph clustering algorithms. ABCD solves a number of problems with LFR, including scalability, for example. Also the fact that it can be analyzed theoretically. Some of you might be interested in that. So we do have a paper analyzing ABCD, the graph version, theoretically. So, okay, so we're going to use this HABCD benchmark, and to make a long story short, there's power law everywhere. That's been mentioned already in great details what power law means. So power law degree, community size, arbitrary edge size distribution. You specify the distribution you want for the edge size, basically. It is that again was as mentioned earlier this afternoon. Sorry, I wasn't here this morning. It's based on the configuration model, and basically once you know the number of communities, it's a mixture of K community hypergraphs and then a background hypergraph that kind of encodes the noise, the noisy part of your graph. So you control a lot of things here. You control degree distribution, community size distribution, the amount of noise that you have. Even your community edge can be a bit noisy with this C and D. Remember the WCD, you don't need to have all strict edges. So all of that can be controlled. Okay, and now starts the experiment. So we want to answer some questions empirically here. So, okay, should we only look at non-decreasing sequences? Well, in general, yes. Again, this is, you know, that's what I should not have done. Control L, right? Okay, so you just don't press too long. If you press more than a second or so, it does that, okay? So just for other speakers, don't press too long. Okay, so essentially, so if in orange here, you have the non-decreasing sequence, and there's just two types of non-decreasing sequence. It doesn't matter really what they are, compared to, you know, sequences of alphas chosen at random. So it means that in the orange, I will have my alpha that's going to be non-decreasing and likely increasing. In the blue, I can zigzag if I want. I can do anything, right? So in general, it's a better idea, you know, to have non-decreasing or increasing sequences. Make sense. That's what we could have just said, let's use that, but we checked, okay? For another type of graph, it's a little less obvious, but, you know, same thing. Yeah, okay. Where should we start from? Oh, that one is interesting. So, okay, this is a Friedman-Nemeni test, but the important thing is that here we're comparing policies. So just think of those are the best and those are the worst. And then this black line represents things that are statistically the same, basically. So there's not a significant statistical difference. So for strict modularity, you should really notice that the first number is always small, 0, 0.25, 0, 0. So you should start, those are the alphas. So you should always start with small alphas for strict modularity. And that makes sense because this is one of the case where it's harder to lift from the ground, right? So, so this makes sense. It's a non-parametric. Friedman is a non-parametric global test, and then the Nemeni does the pairwise comparison afterwards. So it's kind of a step 2. This testing for, if you repeat some policy many, many times, it's rank-based, and are those equivalent or not, basically, statistically significantly different or not. Yeah, so you can look the Friedman rank test. And then the other one, I didn't know about that actually. I learned about that doing this. The second step is to go in a little more detail at the pairwise basis. You know, are those statistically significantly the same or not? Or yeah. Okay. So, right. So now we have talked about the starting point. So we default to starting at alpha equals 0, but if you have, for some of the choices, you can start at some small value of alpha. It doesn't make too much difference. But there are still two parameters that needs to be, and again, this is highly empirical, right? So when should we switch value and change by how much? So in both cases, we're going to parameterize those. We're going to switch values of alpha when the number of communities, because it shrinks, right? It's an agglomerative method. So the number of communities shrinks all the time. And when the number of community reaches a certain boundary, a certain value, n to the power ci, and c is the parameter, the magical parameter we need to find, right? Then we're gonna switch alpha, and we're gonna switch to, you know, something like that. So b is another parameter. Okay. So we're gonna do that completely empirically again, using, okay, this is if we do a grid search, just to show you. And the main thing I want to show you is that, so, 1 second. It's hard to avoid. Yeah. Okay. And it's because, yeah, anyway, you'll see when you're here. So in this case, you see there's kind of a linear thing. So the red are the best policies. So there's a lot of choice here that forms some kind of diagonal. And then, you know, and this is for, okay, a majority HABCD with moderate noise. Okay, fair enough. And then in another case, well, it's similar, but it's not the same. And oh, now it's more like here that's the best, right? Those two that are the best. So in other words, it's hard to tell how we should set those parameters, right? So let's do Bayesian optimization, basically, right? Why not? If you're not familiar with Bayesian optimization, let's say we're trying to fit this, this blue function here, which is the ground truth, which we don't know, obviously. So we look at a few points, the red points, right? And then we get some kind of approximation with a dashed line, some kind of spline, I guess, in this case. This is an illustration from the GitHub repo of the tool that we've been using. And then you have a choice, you know, if you want to maximize exploitation, then maybe you'll choose a point around here because I might get a higher value. But if you look for exploration, there's higher variance here. So maybe you have a utility function that helps you decide, and maybe I should, you know, sample my next point here. That's Bayesian optimization in 45 seconds, okay? But basically, that's what we're going to be doing under the hood. As far as we know, we might explore other methods also. This is work in progress, okay? This is an example for optimizing one of the parameters, for example, C in this case. Fair enough, okay? So, okay. I absolutely hate papers where they propose a measure, a new thing, and then they propose an algorithm to optimize it, and they show that they're the best. Okay, I hate that. I absolutely hate that. So this is exactly what it is. Okay, no, this is just a This is just a sanity check, really. This is just a sanity check. Okay, to see. Okay. If I'm optimizing, so which one gives me the best modularity? This is our algorithm with, you know, the Bayesian optimization and what have you, and it kind of beats the Kumar in a two-section Louvain. Makes sense because they're not optimizing the hypergraph, strict hypergraph modularity. That's not the point that we beat them. It's a kind of a minimal thing that we beat them. Okay, but the main point I'm going to make is this one here. This is with strict hypergraph modularity. And if we start at alpha equals to 1 and we keep there, we don't do that fancy thing in setting parameters and Bayesian optimization, what have you, then it does significantly worse. Again, the scale, don't let the scale fool you. That difference can make a huge difference in the quality of the communities that you find at the end of the day. Okay, so in other words, it seems to make sense what we're doing. And there's a lot more tests that are coming, okay? We want to finalize this auto-configurable H-Louvain algorithm probably using Bayesian optimization, but there's a couple of the things we might want to try. Many more tests using this HABCD benchmark, larger hypergraphs, everything. And of course, test on some real hypergraph and compare with other algorithms with respect, especially compare on equal footing where we do have the real community, the true communities. That's something we can do, right? Although that can be a bit tricky because sometimes the true communities and the ones that optimize modularity are not necessarily exactly the same. So one has to take that with a grain of salt. But anyway, that's a work in progress, and I think I'm right on time. Yeah. Okay. It's the last talk, yeah, but
we have nothing else.
yeah, okay. I'll take questions.